Now, let us look at the last segment of linear phase FIR filters. So, we will look at the frequency response function of linear phase FIR filters. So, all we are going to do now is we are going to take advantage of the symmetry properties that are present and then simplify the frequency response expression, that is all, and then put it in a form that will recall an earlier expression for the frequency representation that we have seen. And one of the representations for the frequency response that we have seen is amplitude times e to the j continuous phase. So, we will put the frequency response expression for types 1, 2, 3 and 4 in that form. We will derive type 1 and then types 2, 3 and 4 you can immediately guess the expression from the form of the answer for type 1. Therefore, we have h of n. So, this is real valued and this is for 0, 1 up to n minus 1, and h of e to the j omega is n going from 0 to cap n minus 1 h of n e to the minus j omega n. And in this particular section related to these expressions, it is customary to denote n minus 1 as cap m. So, whenever you see cap m, it really stands for n minus 1. So, let us look at type 1. Therefore, h of e to the j omega is 0 to n minus 1. So, that is 0 to cap m. So, this is h of 0 plus h of 1 e to the minus j omega and so on. And remember, this is type 1, which means the length n is odd and the symmetry is even. Therefore, if n is odd, then m, which is n minus 1, is even. Therefore, symmetry sample is each of n minus 1 by 2, which falls on a sample, and n minus 1 by 2 is the same as m by 2. So, we look at the penultimate term to the center sample. The center sample is each of m by 2. The previous sample therefore is m by 2 minus 1 e to the minus j omega. So, this is nothing but m by 2 minus 1, and then you have each of m by 2 e to the minus j omega m by 2. The next index of course is m by 2 plus 1 e to the minus j omega m by 2 plus 1 and so on. And finally, you are left with h of n minus 1. H of n minus 1 of course is h of m e to the minus j omega n minus 1, n minus 1 is m. So, this is the expression written out, and now we make use of the fact that h of 0 is the same as h of m and so on, and h of m by 2 minus 1 is the same as h of m by 2 plus 1, and the center sample stays as it is without any counterpart. Now, let us take e to the minus j omega m by 2 outside. So, now this becomes h of 0 times e to the j omega m by 2. If you focus on the last term, this is h of m times e to the minus j omega m by 2, but this is the same as h of 0. So, this is the kind of pattern that is going to emerge, all right. Similarly, you will have h of m by 2 minus 1, and you have you have taken e to the minus j omega m by 2 outside here. So, what will be left when you take e to the minus j omega m by 2 is e to the j omega plus h of m by 2 plus 1 e to the minus j omega, and you have a whole bunch of terms that pair up like this, and one term that is without a pair is this. And now you see the pattern that has emerged. So, you have e to the minus j omega m by 2 n going from 0 to, we will see what the upper index is. The upper index clearly we have to account for this center term h of m by 2 plus n going from 0 to, this term is accounted for. Therefore, the highest index has to go to m by 2 minus 1. Therefore, the upper limit is m by 2 minus 1. This, if you simplify, becomes 2 times h of 0 cos omega m by 2, and let me write down the final expression and you will be able to verify each of these terms follows this pattern. So, this is 2 times h of n cos m by 2 minus n times omega. You can quickly verify that this is true. For example, if you put n equal to 0 here, right, you will get cos m by 2 omega times h of 0, which is exactly this. If you put n equal to 0, you will get the first pair, right. Put the upper limit m by 2 minus 1. If you put n equal to m by 2 minus 1, this will become cos omega, this n will become m by 2 minus 1. So, that is exactly this term, m by 2 minus 1, this plus this will give you 2 times this cos omega. So, this is the general expression for all the terms. And if you see this, this can be thought of as a of omega, because this after all is a real valued quantity, and hence you have h of e to the j omega for type 1 given by a of omega, where a of omega is this quantity I have indicated, times e to the minus j omega m by 2. So, this is the form for the frequency response for type 1, and this is amplitude times e to the j continuous phase. and in this case the continuous phase happens to be precisely linear because that is what the filter satisfies because of the symmetry conditions. Remember, this is type 1, which means even symmetry and odd length. As a simple example, if this were an example of a type 1 filter, length 5, this is the center sample, which is the point of symmetry. Suppose you form another filter G of n, which is you take the original filter H of n, which is type 1, and advance it by n minus 1 by 2 samples. Basically what we are doing is this center sample, which was occurring at n minus 1 by 2, is now shifted to the left, so that this center sample is now located at n equal to 0. Therefore, you are looking at G of n, which is H of n plus n minus 1 by 2, which is the same as H of n plus m by 2, because n minus 1 after all is cap m, and hence G of n is this sequence. Where this sample about which there is even symmetry, which was occurring at n minus 1 by 2, has now been moved to align with n equal to 0. What can you say about G of e to the j omega? It will be a of omega, because G and H are related by a shift of m by 2 samples. If you shift G of n now to the right by m by 2, it will acquire a linear phase term e to the minus j omega m by 2. Therefore, you can think of a of omega as being the frequency response of the filter G of n. And once you see the form for type 1, type 2 is almost can be guessed. It can almost guess the response for type 2. Remember, type 2 is even symmetry, but even length, which means there is no center sample. Therefore, H of omega in this case turns out to be e to the minus j omega m by 2 times, before you had H of m by 2 sample in the expression here, there is no sample for type 2 that corresponds to this. Therefore, that term will be missing. You will find that the expression is again 2 times H of n cos m by 2 minus n omega. The summation goes from 0, before it went to m by 2 minus 1. Remember, m was even in that previous case. Now m is odd, therefore the upper limit goes to m minus 1 by 2. So this is the only change. You can think of this as being a of omega, the amplitude response. Is there a filter or a sequence G of n having frequency response a of omega? The answer is no, because remember, we are now looking at type 2, type 2 is even symmetry and even length. Therefore, here is an example type 2 filter, and the point of symmetry is this, which is midway between samples, and if you call this as h of n, no way can you shift it and have a sequence whose Fourier transform is real valued, because if you shift it to the left, either you will have the case like this, rather. Yeah, one second. It will either be like this or like this. Yeah, question. No, this is m minus 1 by 2. Why did you check? I think this is correct. So, the definition of m is still the same. This need not be an integer. Is that the reason why you are thinking this should be m minus 1 by 2? This is just the argument to the cosine, right. So, that can take on any value. It is not an index of a sample that necessarily has to be an integer. Therefore, yeah, I am glad you asked that question. So, this is not constrained to be an integer, and this is indeed correct. Why don't you verify? I am almost sure this is right. So, coming back to this, you can have g of n like this or g of n like this, and neither of these sequences has a of omega as its Fourier transform. The point is there does not exist a sequence that has a of omega as the DTFT, unlike in the type 1 case where you had g of n when it was the original sequence was shifted by n by 2 n minus 1 by 2 samples to the left, it gave rise to an example sequence like this whose Fourier transform was a of omega. And moment you have seen type 2, types 3 and 4 are similar. So, you have h of e to the j omega. Remember, type 3 is generalized linear phase, beta corresponds to pi by 2. Therefore, you have e to the minus j omega m by 2. You also have e to the j pi by 2. This of course is j times, this is type 3. So, the symmetry is odd and the length also is odd, and the center sample h of m by 2 is always 0 because of odd symmetry. Therefore, that term does not come into the equation. So, you are left with n going from 0 to again m by 2 minus 1, 2 times h of n, and now because of odd symmetry rather than cosine you can expect sine. So, this is 2 times h of n times sine m by 2 minus n omega, and similar to the type 1 case, if you define g of n to be h of n plus m by 2, then you do have a filter g of n that has frequency response given by a of omega. Really it is j times a of omega, because g of n will be real and odd. Therefore, the Fourier transform has to be imaginary and odd. Therefore, the Fourier transform will be j times a of omega. and once you have seen the pattern going from type 1 to type 2, it's easy to see what's going to happen when you go from type 3 to type 4. So, that is h of e to the j omega, this thing remains the same, e to the j pi by 2, giving rise to the factor of j, e to the minus j omega m by 2. There is no center sample, even if center sample were there in the type 3 case, it turned out to be 0. So, this is once again m minus 1 by 2, 2 times h of n, again it has to be sine, m by 2 minus n times omega. So, these are the frequency response expression for the 4 types of linear phase filters. Later, when you take a course, if you at all take a course on digital filter design, when we come to FIR filter design using the Chebyshev approximation, these 4 expressions will be written in a slightly different form, and these 2 expressions can be shown to be equivalent. And the reason for writing this in another form is that there is an associated theorem that requires the expression to be in that form. It so happens that these 4 types of linear phase filters do satisfy that requirement, but before you can be sure that they do satisfy the requirement, you have to write this in the different form that is required for that theorem. So, this is the easier form, the other form is slightly more involved. Once you see that it can be written in that form, all it requires is getting the algebra right. So, with this we come to the end of our discussions on linear phase filters.